Okay, welcome to the particles of matter. We're going to introduce quite a few terms today and think about some crux ideas, differences between them, but we are going to look basically at hadrons and leptons. That's section 6 and section 7. Now, falling into that, we have these other ideas such as baryons, mesons, and lots of ways of making them add up and checking if we can work out what unknown particles may be. So it's kind of the fundamental basic facts about the particles themselves today. Okay, so basically we gave you the hint last lesson. All matter is made of things that are either made of quite heavy things, hence the word hadrons, or light things, which are leptons. Now it's not quite that simple, because if we go back to my cheerful fellows here, all of our particles and antiparticles, whatever type they are, all have different masses. Okay, and it is very specific. It is quantized. So mass is a quantized property, but at a large scale we can't tell because there's so much that matters around it and changes around it. Okay, but we'll look at that. Now, some of them are heavy, the hadrons, because of the ideas from last lesson. All of these quarks are fundamental particles. We don't think they're made of anything else. And when we put them together, they make up our hadrons, okay, our heavy group. Our leptons, they're different. They are fundamental, okay? They're not made of quarks. Now, how do we know this? From results from experiments. Okay, so let's kind of get into the meat of it. Hadrons. Right, there are two types, okay, and the names are hard to remember, baryons and mesons. We'll get used to it, but it is the idea that they are different in their structure, okay. However, what do they all have in common? Well, all of these quark-based particles are all, or can be found, inside the nucleus. Okay, now, the nucleus might need to have a lot more energy than it does at the present earthly temperatures, but we can recreate them if we can concentrate enough energy. So they are effectively the neutrons and protons of this world. Now for us, we only need to worry about two baryons, and those are the protons and the neutrons, because they are so common. There are hundreds of others, okay, but we'll look at the system and how they get there. The other types that go a bit further involve a bit more quirkiness. Okay, so they are not as stable. These are our two most stable types of particles that we know of in the nucleus. That's why you will find protons and neutrons in the nucleus. Okay, so how does it work? Well, they're made up of certain particles, and baryons are all made of three types of quark. Okay, so I'm going to go, it doesn't matter which order you do these, but they are made of the up proton, another up proton, and a down proton. Okay, ud, if you prefer. Whereas the neutron is made of a down, one up, and another down. Okay, so it's two downs and one up quark. Okay, so we've got the information up here. So it's two of those and one of those. Proton is the other way around, two of those and one of those. Now, it's the fact that it's made from these smallest, lightest quarks which makes these two so stable. Okay, now how do they work? Let's just check them up. Well, let's go through the numbers. So up is plus 2/3 of a charge, okay, a charge unit, which is the 1.6 times 10 to the minus 19, so that's 2/3 of that value. We have another of those, and again it's positive, and then a down is going to be negative. Again, we'll check it from up here, negative 1/3. Now if you total those up, 4/3 minus 1/3 is going to give you 3/3, or 1. So that combination gives you the right electrical charge. Now, to make the maths work for when you're looking at this, there's more than just the charge that needs to add up to be conserved. So baryon number is one of them, and it's a simple way to basically say, when I add up all the component pieces, so if I smash a load of particles together, I might get 30, 40, 700 quarks shooting around. I need 700 at the end. Okay, there may be different types and things like that, but the number is still the same. So to do from that, what we have is basically we give each one a third of a baryon. Okay, so its baryon number is a third, positive a third to be exact. And because of that, you need 3 of them to add up to make a full baryon. So you need 3 quarks to make a baryon. So it's just a way of saying that. Now, when we start looking at our other properties, I've got them listed up here: strangeness, charm, bottomness, and topness. As I say, we're not going to look at those, but we will look briefly at the idea, get you the idea of strangeness in there. Neither up nor down particles, up or down quarks, are strange. So they all have a strangeness on 0. Therefore, it's not a strange particle. It's a fairly normal particle. And if we do the same with this, then what we'll find is, again, everything will add up. So downs are minus a third, up is 2/3, get that right, and that adds up to 0. So that combination, just by changing one of the quarks, gives us a completely different total charge. Baryon number, again, they're still the same, which might seem a bit mad, but you'll see when we get to the end how this all adds up. And if you add 3 of them together, you have a full baryon. So protons and neutrons are the 2 that you will need for the exam, fairly obviously, because things are made of protons and neutrons. And likewise, neutron has no strangeness about it. Okay, so that's our big thing. Using our introduction to antimatter, well, down at the bottom here, okay, they're all made from, I should say, they don't have to be quarks. They could be a combination of quarks and antiquarks. Okay, some will make them less stable, but generally the fact they've got 3 and make them quite stable. Of these, of them on their own, protons are the only known stable particle with quarks in. The only known stable hadron. Okay. Everything will eventually decay into this, and the reason is the ups have less mass than the others, and various other factors as well have to come into it. Okay, but basically protons have never been observed to decay when they're on their own. If you put them in nuclei, you can get other effects happening as well, but on their own they have not decayed. And we've done experiments to try this. Some theories say it's millions of years. Well, if it's 1 million years and you have 1 million of them trapped in a tank with detectors round, you'd be able to see one of them decay, or 20 million, 20 of them decay after 1 year. Okay, so experiments like that, I've tried this out. It doesn't seem to be unstable. Neutrons we know are unstable because you learned that at GCSE. Yeah, beta decay is when a neutron changes, and it's actually the change of what they call flavour. The type of quarks have flavours, so the flavour of the quarks change, and what actually happens we'll look into in more detail, but it comes from this. So it's changing from neutrons into protons, and we'll look at why in another lesson. However, just to bring it back, if we were to look at something like the antiproton, okay, it's not the opposite in terms of a pair like up and down quarks. What it is, it's going to be an anti-up, and an anti-down. Okay, so there's still, we tend to use lowercase, sorry about that, tend to use lowercase down here. So what does that mean? Well, we end up with exactly the opposite of every value. So this is minus 2/3, that's minus 2/3, and that's plus 1/3, and that'll add up to minus 1. Okay, so Q equals minus 1. The baryon number, minus 1/3, minus 1/3, minus 1/3, so that's going to equal minus 1. So that tells us it's an antimatter particle. The charge doesn't, because you have positive and negative charges, but this tells us it's an antimatter particle. And then strangeness is still 0. The opposite of 0 is 0, so we still have strangeness equals 0. Okay, and How we tell what particles are is by measuring these values, okay, and then from those values we can work out what quarks must go into them to make them add up. So very similar to chemical reaction. All your elements at the beginning have to be there at the end, recombined and so on, but they all have to be there. So we'll come back to this because we will use this as our definitive thing. However, we're going to introduce the other class in a minute as well. So we'll add in leptons into here. Okay, so it's a nice simple principle. You're just checking your values. Okay, mesons, or mesons if you prefer, are slightly different. So in my diagram here, this is basically your baryon. Over here is a meson, or meson. And the mesons are unstable. And the reason they're generally unstable, or the main reason rather, is that they are always made of a quark and an anti-quark pair. And if you bring that anti-quark near any matching quark, so if you had an anti-up and it came near an up, it would annihilate. Okay, that needs a little bit of energy, again like chemistry, but a lot more energy than chemistry, but you'll get that. So they'll not last long. Okay, so they decay fairly rapidly. And for what we're looking at A level, you're likely to meet two types of meson: pions and kaons. Now you'll meet them because they actually make things happen. So these, although they are particles of matter, they are also what cause forces and interactions to happen. Okay, so it gets a little bit more complicated. So again, I've gone a bit mad with a capital U there. So a pion plus, okay, you just go through your maths from before. You've got your up, which is a plus 2/3, and then your down is a minus 1/3, but it's an anti-particle, so it becomes plus, which adds up to +1. So our charge is a positive charge, just like a proton would be, but it's much smaller, it's less massive because it's only made of two particles. So this middle mass, this meson is the middle layer, much smaller. When we get to some of the bigger particles, the quarks themselves have more mass, so therefore some of them do add up to more than a proton. But that doesn't matter, it's all about counting the number of particles. Okay, if we look at these, the baryon number, well, that's a quark, so that's a plus 1/3. That's an anti-quark, so it's minus 1/3. And that just means that that is not a baryon. So when you add up two quarks, you cannot get them add up to 1. Strangeness, again, we've got 0, 0, and that works in. Okay, now what I want you to do is I'll get you to work through the rest of them, but let's have a look at kind of outline of them. The pion minus is very simply the opposite of what we got over here. So it's a anti-up and a down. Okay, and this is often how the pairing works with mesons. If you do that, you'll find that it should add up to -1. That will still add up to 0, and that will still add up to 0. The pion 0 has an antiparticle, okay, as well. So there are two versions of pi 0. Now, pion is often given the symbol pi. Okay, so if you see that symbol, it'll be the symbol for a pion. Okay, as we got down here. But down at the bottom we have a little bit of information. We got the same effect here. So we got an up and an anti-up, which are going to annihilate if there wasn't other forces going on, and likewise we have a down and an anti-down. Okay, and that will give you different charges. So again, they will add up to 0 charge, so electrical charge is nothing, its strangeness will be nothing, etc. So go through, fill in the gaps, check it all works. That's your background idea that you need to have. Now, when we get onto the kaon, then we have a bit more interesting stuff going on, because they are, of all the ones we need to know, they are the only ones that are strange, that will behave in certain ways. So kaons are always made in pairs, not a pair, but always made in twos, and it's the same combination. They're made with pions, whereas pions don't need kaons to be made. Okay, so when collisions happen, if you make a kaon, you will always get a pion with it. So how does that work? Well, it's got to be different from that, okay, because otherwise it would be a pion. So it has to be an antiparticle. The antiparticle it is a strange quark. So it's an anti-strange. So again, we'll go with the maths of it. We've got plus 2/3, and a strange is minus 1/3, so an anti-one is plus 1/3, and like before, it's just going to add up to +1. Okay, so you can work through the ideas, that one as well. The crucial bit is this antiparticle has a strangeness of 1. Okay, let's put the +1, whereas a strange particle has a -1, whereas an anti-strange has a +1. Okay, and the up and down don't, whether they're particles or antiparticles, and so on and so on and so on. Okay, so we can work it through. The crucial bits is when we're checking equations, we need to make sure charge is conserved. So all of the quarks need to be there because that will happen. You need to check whether you made baryons by getting a baryon number of 1, or not baryons, mesons, which means it adds up to 0. Okay, so this is how we check what's being conserved or not. Strangeness is a bit different, as you'd expect from the word strange. And the crucial point is it all depends on what you're doing with your particles. If your particles collide, then we just check everything adds up. But if one of your kaons, one of your strange particles decays, okay, so it changes into a lower energy state, a more stable state, if it changes what it's made of to make that happen, what you'll find is strangeness changes, the value for strangeness changes. Okay, so we've got this happening all the time. Collisions, decays, just like any other chemical reaction, you're breaking apart our structure, rejoining it in different ways. But when it decays, then you've got a slightly different effect going on. Okay, so it's kind of a cross between decay and biological matter, but it's actual physical matter. Okay, so crucially, in terms of in the exams, you don't need to know the quark combinations, but fairly straightforwardly, I think, because protons and neutrons are just ups and downs. Pions are just ups and downs. Okay, if you remember the zeros, maybe the other pair, particle-antiparticle pairs, you know, kind of useful, but mainly it's just the fact they're ups and downs. Kaon is the only one where you have your strange particles in. So again, just check all the mesons, antiparticle, particle, antiparticle, particle. And this one must be the opposite, so what you've got here is a down and an anti-strange. Okay, so other little minor point, notice they're the same quarks, quark, antiquark, they're not. Okay, so there's no special pattern about the kind of names, oh it's a kaon 0 or an anti-kaon 0 or whatever, it's just making sure everything adds up. So everything will add up to 0 in these because there's 0 charge, 0 electrical charge. Okay, but strangeness charge, and if we were to go further, charmness, topness and bottomness would also have special rules that govern them. Okay, now we'll introduce you to leptons and the term about the Quibbles law. Okay, so we looked at Q, B and S, electric charge, Q, baryon number, strangeness. We're going to look at leptons as well, which gives us a nice little quibbles. It's a bit you know, BBC One humour, but there you go. So, Blackadder, come save us. So, part 7, much shorter. There's much less complication. There are, if we took all 6 combinations, all 6 quarks and put them in all the combinations, you can do the mathematics of that. Okay, if we didn't have antimatter, that would be 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. that would give you the number of combinations of hadrons, particles with quarks in, that we could make. Okay. However, there are combinations and restrictions and all the rest and general rules, so we have not observed all of them. Leptons are much simpler because they are not made of anything else. These are fundamental. Okay, so fundamental is an important word. It just means it is the simplest thing. Fundamental frequency, the simplest frequency, the lowest frequency. Yeah. Okay. We'll come back to those. Please notice that's not baryons. Okay, useful word, but you don't need to learn that one. We'll come back to that. So, leptons are very similar. They're subject to the same rules. They are also affected by a lot of similar things. There are actually only 4 things that affect everything, and 3 of them affect both hadrons and leptons. The 4th one doesn't. The 4th one is the nuclear strong force that we looked at the other day. It's what holds the nucleus together. Leptons are not found in the nucleus, or if they're there, if they've suddenly been made during a reaction, they won't stay there because there's nothing to hold them in. Okay, so quite simple, little particles, very light, and the reason is because they are very, very tiny. We've never actually measured the size of them, but we have measured their mass. Okay, so what are they? Electrons. Its heavier brother, shall we say, called muons, and the heaviest is the tauons. Okay, so again, mu, leptons, tau, leptons, electrons. You could call them out, but most people will call them electrons, muons, and tauons. Okay, so electrons, I'll just put the symbol at the top, E. We have our muons, using the symbol mu, and tau for tauons. Okay, so that's where your symbols come in and where you will see them written in the equations, just like with chemical formula. Okay, because these two are more massive, they're less stable than electrons. So if there's not enough energy, that will decay into that, or that will decay into that. So they're just heavier versions. If you've got enough food to sustain them, shall we say, then you can make that heavier version. Okay, in terms of the details about them, fairly straightforward. But, and this actually makes it easier, of the 6 particles, they actually come in 3 pairs. Okay, and the pairs are that you always have a neutrino that goes with the particle. So electron has a neutrino, electron neutrino, so a little subscript E. A muon has a mu neutrino, a subscript mu, and tau subscript T for a tauon neutrino. Okay, and again, the symbol's not very obvious there, but they're quite curved. So that's your symbol for a neutrino. Okay, mentioning something else up here. I'm going to leave it for this lesson. We'll come back on another time. But there is another type of nuclear force that does affect these. It's a bit more complicated, so we'll leave them. It's kind of a minor idea for us. Last thing is, neutrinos were really, really, really difficult to find because they have such a small effect on things. They shoot out from nuclear bombs, they shoot out from the stars, including our sun, all the time. They go through the Earth without interacting. They're so small in mass, they almost don't affect anything. Okay, the crucial bit is, as it says, it's almost impossible to detect because of that fact that it has almost no mass and it has no electrical charge. So chargeless, the others are all negative. Just like the electron is negative, the older, heavier, more massive versions are also negative. So let's just go down that list a second. That'll be -1, 0, -1, 0, -1, 0. Okay, and if we were to consider these, and we will consider these much more than we will the anti-hadrons, the versions with quarks, opposite of quarks, to protons and neutrons, for example. These we will look at quite a lot. And again, it's just the opposite charge. So +1, 0, plus 1, and again 0 is the opposite of 0. Lepton number is also what we've known as a quantum number. It's a representative number that has a definite value, can't be part. So again, like the baryon number, all of these are not leptons, so they're all negative values. Positive values are leptons. So if you had 20 leptons at the beginning, you need 20 leptons at the end. Or rather, they need to add up to 20 leptons. So you could have 21 leptons and 1 anti-lepton, because that will still add up to 20. Okay, so that's how the kind of mathematics of it, and it's all down to these conservation laws. Okay, so I'll just put this bit in brackets because that's quite rare for our course. It's more in some of the other courses. But basically, this is what you need to do. You need to look for these quibbles. And this is how you break down the answers. I'll give you an example in a second. So you need to check the electric charge is conserved. The baryon charge or baryon number is conserved. The lepton number is conserved. Okay, so again, even though you have made them react and things change, they're still there, as are the leptons. And then strangeness, which usually is conserved when you have collisions. That involves certain forces. Okay, so when things collide, they repel and stuff like that. That's an electromagnetic force. Coulomb and magnetism joined together force. And the strong nuclear force. Right, let's work through an example. Skip back to this in the next thing. And here is one example, and this is the idea of pair production. So you've got a single photon whizzes in, okay, and that's let's go with our picture. So our gamma ray comes in, it creates a pair of particles that shoot off back to back, blah blah blah. So that's what we got here. They're making a pair, so it's an electron. I'm going to call it electron minus to show that it's an electron, and electron plus, or anti-electron. However, putting the plus and minus really helps with all of these. Okay, so let's run through the process. We're going to look through and check quibbles, what is conserved and what isn't. So, does a photon have charge at the beginning? No. Is it a baryon? Is it made of quarks? No. Is it a lepton? It's not on my list. No. And it's definitely not strange. It has it doesn't involve strange quarks, so if that's 0, then that's got to be 0. Now, in terms of charge, we have -1 there. And again, electron is not a baryon, but it is a lepton. Okay, and it's not strange. Okay, none of these are strange. Only the strange quark is strange. Here we've got an opposite charge, as you can tell because it's plus. So it's got an opposite charge of +1, or 1.69 10 to the -19 to be exact, but again we're going to use relative charges here. It's not a baryon. It is an anti-lepton. Okay, so it's -1 score, and it has 0 strangeness. And what that means is, and we can fill it in here if you want, but basically 0 goes to 0, 0 goes to 0, 0 goes to 0. Why? Because it's +1, subtract 1. You end up with 0. So basically all your laws are conserved, they are obeyed. That means, assuming you have enough energy, this interaction is perfectly possible. And that's what you're looking for when you do this. So, let's look at another one. And this is now starting to move you into the more interesting bit. It links in with the radiation and so on. So, here we have beta decay. Okay, or beta minus to be exact. Okay, we're going to get into more detail. There's 2 types of beta. What has happened? Well, at GCSE, a neutron decays into a proton and an electron. Yeah? So, let's just check. We have no charge on a neutron. Sometimes they write with the 0. Sometimes it's worth putting that plus on the top just to help you. Doesn't really matter too much. Is it a baryon? Yes, it is. Is it a lepton? Well, no, because it's a baryon. Okay. If it was a meson, both of those would be 0. And it's not strange. Okay, so its charge is +1 on a proton. It is a baryon. Okay, again, if you want to put the plus, it helps. It's not a lepton because it's a baryon, and it's not strange. Okay, whereas an electron has a minus charge. Great, so that's conserved because 0 adds up to 0. It's not a baryon. Okay, so that's a 1 going to 1. That's okay. Just put that in. It is a lepton, and it's actually a lepton. A normal particle matter is an electron, so that's a +1. So we've got 0 becoming +1. Okay. 0, strangeness, so 0 goes to 0. That's fine. That isn't working. Okay, so what you were taught at GCSE is fine up to a point. We know that the charge must conserve, so you had no charge at the beginning. These two add up to no charge at the end. But there's something missing, and this is the kind of thinking that goes into, well, what is our missing particle? So if we look at this, okay, we need a particle that has no charge, no extra value here, so it's not a baryon. We need a -1 lepton number to add up to 0 and a 0. So 0, 0, -1, 0. So we need an uncharged anti-lepton to make this add up. Okay, and ignoring that idea of the total energy or mass energy and momentum that you always have to have conserved because that's just down to movement. What we need, and matter, we need to look in for all this missing particle, of which led us to the value of neutrino. Okay, so that is an example of how we start going into extra things. So our X particle will need to be 0, 0, -1, 0. And if anyone can look at that and then go, this sentence is not quite true, well done, you've spotted it. Okay? You can correct that. Okay, so this is how you go about it. Right. Look for the clues about charge. That's the easiest thing to spot. So is it plus or minus and do they add up? That's fine. Baryon number, it means the number of quarks is right. Okay, so leptons and mesons don't have a baryon number, it's 0. If it has a lepton, then it's a lepton. Okay, so it doesn't involve quarks at all. So the baryons are the ones with quarks in, the mesons are the ones with quarks in, leptons are not. And yeah, you don't need to worry about strangeness too much because it's pretty rare, but it may be mentioned if they have a strange quark. That's the thing to remember. If strangeness gets mentioned, you've got a strange quark in it. Okay, and those are the two big chapters on our factual knowledge. So a bit of a long walkthrough, have a work through those other questions, but we're going to use them in our next session to actually look at why things happen.